Alrighty, we're going to go ahead and get started with lecture. The first thing I want to point out to everybody is that I've posted some instructions on installing Cplex. So for starters, please make sure you follow those instructions to the T. So it involves setting up an IBM account, registering, making sure you're registered as an academic account. And then I would definitely recommend using the links that I've provided. And that should get you most of the way there, because what happens is if you don't download the academic version, then you're not going to get the full version of Cplex, and it'll only allow you to develop programs with 100 variables or 100 constraints or something like that. And for the project, you're going to potentially have hundreds to thousands of constraints. And so the let's say restricted version of Cplex isn't going to do you any good. So please make sure that you have an academic account with IBM and that you sort of follow the directions. I think they're pretty good. And they'll get you most of the way there. At that point, you should be able to install and run Cplex. There might be one or two little weirdnesses if you want to use Python. That's certainly an option. So I'll post a quick little note maybe on those folks who, as part of their research, they use Python and Cplex, especially in a Windows environment. In a Linux environment, it's a bit easier. But I think for the most part, everybody will be okay because we'll be using the Cplex Optimization Studio. And then additionally, with that in mind, I think it will be worth students' time going through the videos that I've posted on how to use Cplex. But for now, I think, and I'll post an announcement on this, so you don't need to start running on Cplex right away. But definitely get it installed, over the weekend. And next week, I think learning to program a very basic linear program into Cplex will be useful for a variety of reasons. One, it lets you check your work. So like you can solve everything manually as part of the homework and do sensitivity analysis as part of the homework manually, but then check your answers using Cplex. And so that's, how I'd recommend everybody use Cplex, at least at this stage, before we start doing some serious programming. Okay, with that, I'll go ahead and get started. I'm going to be lecturing off of the sensitivity analysis and duality set of notes. And we're going to start by sort of relating sensitivity analysis to the Simplex tableaus that we're going to be working with. Can I hide this? Leave it at that. I always forget how to do this. Oh, there we go. Okay. All right. So all this conversation is going to start with one basic assumption. And that basic assumption is that we know the optimal basis, or we have a set of basic variables. And I'll say potentially optimal. Well, we'll just start with a basic variables. That are potentially optimal. So this is sort of the framework that we're going to be working in. Okay. All right, so we're going to sort of jump right in to where we're headed by using an example problem, and that will motivate a lot of the work. All right. So let's start with a maximization problem. And I'm going to structure it so that I've written out most of the problem, and we've already figured out what the slack variables are. Okay. So here I have 0 times S1 plus 0 times S2 plus 0 times S3. And I think there's the same problem that we use in a lot of the example problems. I don't quite remember. And I'll try to make it sort of look like it's in matrix form almost, right? So I'll align all the decision variables. All right, so we're going to start off with this basic problem, or example problem that we're used to working with. And we're going to assume that we already know a basic feasible solution. Right? So here goes our problem. All the xi and si are greater than or equal to 0. And we're going to begin with the knowledge that our basic variables is the set S1, X3, and X1. And so that means our non-basic variables are all the others. So we'll put these down as X2, S2, and S3. You can order these as the set. The reason why I'm listing them the way I'm listing them is because this ended up being sort of one of the solutions at one point to the example problem when we looked at a simplex table. All right. So with this in mind, we can sort of rewrite this problem in terms of what is a basic variable and what is a non-basic variable. Okay. So what I mean by that is we're going to define a vector xbv, right? Where inside that vector, we have all our basic variables. Right? And we'll have an x nbv, which is the non-basic variables. So before we just had a vector that was x1, x2, x3, s1, s2, s3, right? So here we're going to rewrite it by sort of defining these new vectors, or rewrite our problem. Okay. All right. So with that in mind, we can sort of say, well, let's, the cost function is pretty easy. Our basic variables, not that guy. Our basic variables are S1, X3, and X1. All right. So if I want to rewrite what this maximization looks like, it ends up looking like max 0, 20, and 60 times the vector S1, X3, and X1. Right? And again, we're just getting that from the 60, 0, and 20. But we have to reorder it according to the order of the decision variables. All right. So the next part of it will be the cost function according to the non-basic variables. Right? So if we look at everybody else, and I'll denote it in green, we have 30, 0, and 0. All right. So with that, Okay, so again, we have our XBV and our XNBV, so our non-basic variables. And similarly, we can split up our C transpose, right, into two parts. So this is our C vector corresponding to the basic variables, and this is our C vector corresponding to the non-basic variables. Okay, all right, so we're going to apply this similar idea of splitting up our data into two different parts, our constraints into two different parts. All right, so again, we'll sort of split it into, normally we would have AX is equal to B, right? But we're going to split this up into two constraints, or sorry, two parts for the constraint equations. It's still going to be the XBV. Plus some equations related to the non-basic variables. Now, we haven't actually changed what the constraint equations are. They're still equal to whatever our B matrix is. So if we go back to the problem, or B vector, we go back to the problem, our B vector is just 48, 20, and 8. Okay, so the question is, what goes into these matrices, this A that we end up splitting apart? Okay. All right. So what we're going to do is we're going to take the values of the matrices that correspond to the basic variable. So first we have the column corresponding to S1 because it's a basic variable. Then we have the column corresponding to X3. And finally, we have the column corresponding to X1. So we're going to take these parts of the constraint equations and put it in the first matrix. So when we do that, and it's a little bit out of order, again, because we started with S1. So we start with this guy here. So it's 1, 0, 0. And then we have 1, 1.5, 0.5, and finally 8, 4, 2. Okay. Similarly, we do this with the non-basic variables. And so when we look up at our problem and the corresponding columns to each of the decision variables, we get the following. Now we're going to name these matrices, or we're going to give them like a special variable name. So we'll call this guy capital B and this guy N. And again, the way that you can think about this is the A matrix for the basis variables. Or basic variables. And this is the A matrix for the non-basic variables. All righty. Now, originally, when we solved this problem in a previous class, we ended up with a simplex table, right? And let's see if I can find it. I might be able to find it. Let's see if we can find it somewhere. Simplex method, by example. Is this it? Yeah, so this is the original problem. So I'm going to go ahead and let's see if I can find the final solution. This might be the final here. Yeah, I think this is the final. Okay, so this was the final simplex table that we ended up with. Now, this simplex table was generated from the initial formulation. All right, so how did we get there? And what does this final formulation look like if we sort of put it into this form where we split up our variables into basic variables and non-basic variables? All right, so the equivalent formulation, we could just go through this matrix or this tableau and fill out what the formulation looks like. So I'm going to make this a little bit bigger so it's readable. So that's a little bit readable for me. Okay, and again, in this case, what we ended up with was S1, X3. So S1. Oh, wait. Seems like I'm missing a step. X1, S3. Oh, why did I copy the wrong table? That doesn't make sense. I need to get the very last one. X1, X3. There we go. This is what we wanted. My apologies. So this is the final table. So S1 is part of our basic variables. X3 is a basic variable, and X1 is a basic variable. And again, we sort of see the structure of the basic variables where we have 0, 1, 0, 0, 1, 0, 0, 1, 0, right? So that's sort of the indicator. If I were to just look at the table, I could figure out what the basic variables are. So we can rewrite this problem by splitting it up into the basic variables and the non-basic variables, just using the Tableau. So if we were to do that, we would still have maximize, okay, and we'd get 0, 0, 0 for the cost function. And we get that by looking at the coefficients of each of our basic variables, okay? And again, they go in order from S1, X3 to X1, so they're a little bit backwards. We then have the decision variables that correspond to the non-basic variables, and those are X2, S2, and S3. For those of you who are wondering, how did we end up with the order S1, X3, X1? It's because we see the first one, the highest row, I guess, where you have a 1 is S1. And then the highest row where you have a 1, the next one after that is X3. And then finally X1. So that gives you a little bit of an ordering, if you'd like it that way. Okay. But again, you can always reorder the XBV variable as you wish. But that's sort of where I'm taking it from. Okay, so next, if we look at the non-basic variables and the coefficients, we have 5, 10, and 10. But we have to be a little bit careful because these are actually the negative of the coefficients when we write out our problem. So in fact, here we have -5, -10, and -10 getting multiplied by the non-basic variables. using the Tableau, we can do the similar procedure for what the constraints look like. So, you know, for the B matrix, it's pretty straightforward because each one of these is going to have that 0, 1, 0 structure. Let's see. So how do we do this? Oh, I feel like I did this in the wrong order last time. 0, 20. All right. So here we should have 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Right. And that will give us the first part. Next, we have to pull out the constraint equations corresponding to our non-basic variables. So for x2, we should have -2, -2, 1.25. Right. For the next constraint, we go over to the variable s2 and we just read down the columns. So here we have 2, 2, -0.5. And then finally, this last one, we have S3. I'm not sure what this column was. I think let's just ignore that. I think we added a constraint or something. The next one is for S3, and we have -8, -4, and 1.5. Okay, so this is the same formulation. Oh, and it's all equal to 24, 8, and 2. All right, so the interesting part, or not so interesting, I mean, it sort of makes sense, is this is actually, we'll give, if you were to optimize it, which it's already optimized in some way, because we know S1, X3, and X1 is equal to 24, 8, and 2, because it's the solved simplex table, that will actually be the same solution to this problem here. It's just we haven't gone through the simplex method yet. So this was before simplex. And here, this is after simplex. And again, because all we're doing is elementary row operations, we actually haven't changed the problem or changed the solution. So what we want to do is we want to relate these two formulations to each other, okay? So we want to look at how do we go from the CBV here to getting 0, 0, 0 there, right? Same thing with the CNBV, right? So how do we go through this transformation? And information on how we go through that transformation will actually provide us with the tools we need to do a sensitivity analysis. All right, so let's sort of look at what ends up happening, right? And what is the relationship between one sort of formulation and the other. Again, they represent the same problem. All right. So originally, let's just look at the constraints. So we're going to focus on the constraints. And this is for the original problem. So based on the variables that I sort of defined, right, this B, XBV, N, and so on, the constraint equations we can write as the following set of linear equations. B times XBV plus N times XNBV equals B. Now, we know in the end that somehow we're going to rewrite this equation so that if we look at this part, right? So this is the equivalent of this part right here. We're no longer multiplying times B, but instead we're multiplying times the identity matrix. So we want to replicate what that looks like, right? And the way we can replicate that is by multiplying both sides of this equation by B inverse. Right? So we're going to multiply times B inverse. So when we end up doing that, we get, B inverse times B XBV plus B inverse times N XNBV equals B inverse times B. Going through that multiplication, we just end up with I XBV plus BN XNBV Now, what does this B inverse represent? Well, B inverse, that just represents all the elementary row operations required to get your simplex tableau to be in that form where we have the 1, 0, 0 and 0, 1, 0 and 0, 1, 1, whatever, 1 for our basic variables. So when we're getting into that simplex form, right? The solution. All right, so this is pretty cool. All right, so let's apply that to the case that we have at hand. All right. So in our case, our B, let's see if I can, our B was 118, 0, 0, 1.5, 4, 0.5, and 2. Okay, so the first thing that we're going to do is we're going to solve for B inverse. And you can just do this using something like MATLAB or Octave or Mathematica, I suppose. I'm sure there's a bunch of different languages that you can do it, or your programmable calculator. That's certainly fine. So in this case, B inverse is equal to 1, 0, 0, 2, 2 minus 0.5, and 8, negative 4, 1.5. Okay. All right. So at this point, we can sort of start filling things in our equation. So we still have I times XBV plus B inverse. So 1, 0, 0, 2, 2, minus 0.5, 8, 4, 1.5. Right, so this is our B inverse. So we're applying equation star. All right, so we got the B inverse. The next thing we need is N. All right, and so we had written out N before. So N is this guy here with the 6, 2, 1.5, 0, 1, 0, 0, 0, 1, right? So it's this guy here. So we can go ahead and just fill that in. Everything gets multiplied times X and BV. And again, it's going to be equal to B inverse times some quantity. And in this case, that quantity we're going to multiply times is the right-hand side B. Of our original formulation. So if you go through that process, you end up with the following. So again, we have 1, 0, 0, the identity matrix. If you multiply B inverse times N, you get the following matrix. And sure enough, this is what we had in our Cplex table. Okay, so I'm gonna, as the refresher, that was basically what we got here. So again, if we know the basic variables, we can actually reconstruct our simplex table pretty quickly. I don't remember what this last row is for, so I'm going to delete it. And all we haven't really dealt with this one here, this column. So I'm going to try to white it out. So we see the diagonal matrix. Again, that's going to be coming from our basic variables, S1, X3, and X1, right? So those are the columns that we have, right? And then for the these guys right here, we also see these same columns in the simplex table after we perform all our elementary row operations. So some of you might be wondering, well, why did we do all these elementary row operations by hand if we could have just taken B inverse? Well, the problem is we didn't know what the final optimal basic feasible solution was, right? That was the whole point of the simplex method, right? But all I'm showing you here is if you know what the optimal basic feasible solutions are, then you can reconstruct your simplex table, and we have the corresponding equations on how to do that. Again, this is going to become helpful as we start doing our sensitivity analysis, because what we're going to do is we're going to talk about, well, what happens when we change CBV a little bit, or what happens when we change CNBV a little bit, or what happens when we change the right-hand side a little bit. We're going to be able to track those changes of what happens using the equations here. Now, we've done the first step of sort of figuring out our simplex table through the equations with the constraints. But what's missing here is we don't know what's going on in row 0. So our next step is to try to figure that out. What does row 0 look like? All right. All right, so we have a few equations that we can use in order to solve what row 0 ends up being. So the first one is, what does our original row 0 start off as? And again, we're going to reference back. So this equation right here. Right? So we have CBV times XBV. Right? CBV times XBV plus CNBV times XNBV, and all this is equal to Z. Right? So if we shuffle things around, we can rewrite that as Z minus CBV times XBV minus CNBV times XNBV. And this is all equal to 0. Now, we have another set of equations that is going to be useful in order to get the sort of form that we want, okay? And that other set of equations is the constraint equations. So our constraint equations start off as B XBV plus N X NBV equals B. Okay, so these are the two sets of equations that we're going to use in order to calculate row 0. All right. Now, this is going to take 2 steps, and essentially what we want is, we know that for our basic variables, okay, so in row 0, S1, X3, and X1, this is going to be equal to 0. All right. So we know that's going to be equal to 0. And so what we want to do is cancel out, in some ways, the XBV. Right? So when we look at this equation, right, we're going to do some manipulations to it, so XBV isn't part of it anymore. And the way that we can do that is by subtracting these 2 equations from each other after some row operations. Right? And so the way that we can go about doing that is, we're going to take our constraints equation and we're going to multiply it times B inverse. Right? We're then going to multiply it times C BV. And we're going to add these 2 equations together. And in the process of doing that, we're actually going to cancel out this CBV times XBV. So the end result, so after we do that multiplication and addition, we end up with Z. Actually, maybe I can do a few more, well, I'll do a few more steps just so you can see it all worked out. All right, so we're going to add these things together. So for starters, we might as well just do the multiplication. So when we multiply this first quantity, the B's cancel and we end up with just CBV times XBV. The next part, we end up with CBV times B inverse times N XNBV. And finally, for the right-hand side, we've got that. Okay, so at this stage, we can add these 2 equations together and we see these 2 guys cancel out. All right, so after adding them together, we get Z minus CN BV XN BV. All right. So the nice part is we can do a little bit of factoring. All right. So when we do our factoring, we can factor out the XNBV term, right? So they have this in common. And I'm going to do a little bit of light reorganizing. So I'm just going to switch the location of these two coefficients so I don't have a minus sign leading. So I get CBV times B inverse minus C NBV. Actually, I forgot it. Missing an N. All right. So this is sort of our final equation that we end up with. All right. So what I want to do is focus in on this part right here. So this part right here is going to have the coefficients of the 0 row. All right. So this is the coefficients of row 0 in the Simplex Tableau. And this is going to have the optimal solution. Or the optimal value, sorry. Okay. All right, so we're going to focus in on the coefficients part, because this is actually a vector. Okay. All right, and this is a scalar. Okay. And it sort of makes sense. We have a vector here times a vector. Essentially, we're taking a dot product. And so that's why we end up with a scalar. Okay. So one thing that we can do is we can sort of focus in on an individual variable. Okay. And so what does this sort of look like? What do I mean by that? Well, if we have CBV, that's not going to change. B inverse. But let's say I want to look at what's the coefficient for the ith variable of the table, right? So the coefficient of ith variable, and actually it's for the non-basic variable of the table. Well, that corresponds to CBV times B inverse times the column of n for xj. So whatever that, that variable is. So this is the xj column, right? So they don't always align, right? The coefficient of the ith NBV is not necessarily the ith column of the table. So just maybe that might be a little bit confusing, but it sort of makes sense. And that just comes from this part of the equation right here, right? So from this guy here, oops. We're just focusing in on one variable. Similarly, we can do the same thing on this side. We just end up with the coefficient for xij, or for xj in CNBV. Now, all that, right, we can set equal to, not set equal to, that's the same thing as just writing CBV, B inverse, times AJ, right, minus CJ. Okay, so what is this AJ? So AJ is the jth column of our original A matrix. All right, so let's sort of see how this plays out by an example, because I think that makes a little bit more sense. All right. So in our example, our CBV was equal to 0, 20, 60. We had already solved for B inverse above, so I'll just sort of rewrite that equation, or the values. Okay. And then the corresponding N matrix that we started off with. Okay. So if we want to calculate the 0th row, right? So the cost row, all we need to do is essentially apply this equation here. Okay. So we take CBV times B inverse, and then we subtract, times N, and we're going to subtract CNBV. And so that means we need to know what CNBV is. Where's my CNBV? Ah, here we go. So this is my, oh, that's not the original. Here we go. It's the 3000. All right, so if you multiply all this stuff out, so again, I'll just be explicit. So we're going to fill in the following and multiply everything out. Actually, you might as well do this in Octave. So I don't know. There's a few different ways we can do this. So I'm just going to show you guys. Sometimes I use Octave Online. Maybe you guys find that useful. I don't know. Let me see what that looks like. So if you guys are used to using MATLAB, you can certainly do that. So there we go. So here goes octave-online.net. And so we can sort of test this out and figure out if we get what we expect. So I'm just going to define these matrices. So I'll have CBV is equal to 0, 20, 60. All right, CNBV. What is that equal to? I think 3000. And then finally, I'll actually type in B and then calculate the B inverse. You guys can sort of see me work through the whole process. So for those of you who don't know, haven't programmed in MATLAB or Octave, I think sort of tracking what I'm doing along you know, it'd be sort of good to, well, I don't know, I find it useful. I think MATLAB's easier to work with than a calculator. So you define matrices by just saying the variable name equals, and then you put square brackets. You type in your elements with spaces between them, and for a new row, you just put a semicolon. So when you do that, here goes our B matrix. So if we want to calculate B inverse, we just say inverse B. So that's what we had before. And then we need our N matrix. So our N matrix in this case is 6, 0, 0. Oops, and I need square brackets. Semicolon 2, 1, 0, semicolon 1.5, 0, 1. Okay. So let's sort of apply the equation we just learned, which is CBV times B inverse times N minus C and BV. Okay, so we end up with 5, 10, 10. And this is exactly what we expect to get, right? So in our original formulation, when we had solved the simplex table, you can see if we look at the 0th row, we see 5, 10, and 10, and then everything else is 0, right? Except for Z here. And so that's one way, if you know your optimal basis, or you know the basic variables that you want to use, then we have a way of calculating what your simplex table is after your elementary row operations. Right? So again, after applying this equation, we end up with 5, 10, 10. And with that, we can fill in the missing elements of our Cplex table. So here goes the recalculated Cplex table. Right. And again, we sort of said, well, we know that for our decision variable, our basic variables, S1, X3, and X1, that those are, or by default, they're going to be 0, right? So we knew this was going to be 0 for that row 0, X1, and X3. So what are these guys here? And so we're able to fill in the rest of the table using the equation above. All right. So moving forward, we're going to call this new row after the equivalent, let's say, elementary row operations that we apply. We're going to call it C bar. Okay. And so one thing that we often write is we write C bar J, again, is equal to CBV times B inverse times AJ minus CJ. Okay. And again, this AJ and CJ just come from the original formulation. So you can think about the problem in terms of like CNBV, CBV, BN, capital B, capital N, or you can go back to the original formulation and just pull out the jth column. So what do I mean by that? So this is the first column here. Oops. You know, first column, second, third, fourth, and so on. So that's sort of what we're talking about. It's just pulling out the column. But depending on how you're doing it, if you're just referring to N and B, then it sort of makes more sense to just use the equation here. Okay. That way you just get them all at the same time right? So this equation is like the one at a time way, right? Like the algebraic way, I guess. And this equation here is like the matrix equation. The same idea, right? But one sort of just does them all at once. All right. So with that in mind, you know, based on the equation here, we see that C1 is equal to 0, C2 is equal to 5, right? Because we got that from there. C3 is equal to 0, C4 is equal to 0. And I should put bars over this. And again, the reason why the first, third, and fourth are equal to 0 is because these correspond to basic variables. Okay. Meanwhile, C2, C5, and C6 are equal to 5, 10, and 10 respectively. Okay. So the other question is, well, if we know our basic variables, we've almost solved everything. So we figured out how to calculate the part of the simplex table corresponding to the constraints. We got that. We just figured out how to calculate the row 0. Okay. The only thing that's missing is how do we calculate what the cost is? Okay. And we have an equation for that. That was part of what we solved. Okay. It's given by the CN or the CBV B inverse B here. Okay. So we can go ahead and just plug that in. Right. Of course, we already know it's 280 because we've solved this problem before, but let's pretend we hadn't solved it before. Okay. What would we get? Well, so we're going to do CBV B inverse times B. Okay, so I'm just going to go, we could certainly write this out. So it'd be 0, 10, 10. Oh, not 0, 10, 10. Sorry. So what's CBV? 0, 20, 60 times B inverse times B. Right. I always forget what B was, and I have to look it up again. Okay. So all we have to do is calculate this matrix equation. And again, we already have most of these values programmed in into Octave. We're just missing the B vector on the right-hand side. So I'll just type that in, 48, 20, and 8. Okay. And so we can calculate the cost by multiplying CBV times B inverse times B. There we go, 280. All right, so this is what we expected, right? Because we already solved this manually. So we have this guy. All right, so let's take, actually, okay, we're going to just do a quick example problem and then we'll head to a break. All right, let's do the example problem. All right. So let's imagine the following optimization problem. So it's just two variables. Or at least it starts off that way. Now, the first thing that we're going to have to do is we're going to have to put it into the standard form that we expect so that we have only equality constraints. So right now we have inequalities. So we're going to rewrite this and we're going to add in our slack variables. Okay, so let's pretend I gave you the optimal basis.
This formatting for objective function.
Excuse me?
It is for x2 for objective function.
Oh, yes, thank you. Thank you. I missed that. Yeah, thanks, Alsaid. So let's say I gave you the optimal basis. And we'll say the basic variables. So we're going to say it's x2 and s2. All right, so if we're going to put this, the original problem in matrix form, and then I'll show you how we break it down. We would have 1, 4, 0, 0 times x. And here, x is equal to x1, x2, s1, s2. Okay, so it's going to be our vector of our decision variables. All right, and we're just trying to get it into C transpose X. Into that form. Okay, so our constraints, again, we sort of can just read them off the equations. Doesn't take too much thought. Okay, so we're going to start off like this, and of course, X, we have a non-negativity constraint so that all variables in X are greater than 0. So if we do this and we say, well, we know X2 and S2 are our basic variables. So that corresponds to the following column. So we're going to take 4, 2, 1, 0, 0, and 1 in order to define our B and our C and BV and all this stuff. Okay. So for starters, we can start with CBV is equal to 4, 0. CNBV is everything else. So it's 1 and 0. Right. Our B matrix, capital B, is 2, 1, and 0. Oops, 2, 1, 1, 2, 1, 2, 1. Oops, 2, 1. Yeah, 2, 1, and 0, 1. Okay, so again, that's just, I'm just taking these rows out. So here, going to put in there. And this guy's oops. It's getting put in there. All right, similarly, we can define our n matrix, sort of everything else, right? So in this case, our n is 1, 2, and 1, 0. Okay, and that just corresponds to that column and that column. All right, and lastly, our b is just as before, 6 and 8. And so with this information, the question is, can we solve for the optimal tableau? Okay, so we want to fill in what the tableau looks like, knowing that x2 and s2 are our optimal solutions. So we're going to apply all the equations that we've learned. So let me sort of remember them all and get them written out that we can find them. All right. So let's write this out. So let's say we have our optimal tableau. So we're going to have x1, x2, s1. We'll put in z there, s2 equals. All right. So the question is, what is row 0? Well, row 0, we know x2 and s2 are basic variables. So we know they're going to have zeros in them. The question becomes, what is in the row for x1 and s1? Okay. And the way we calculate that is just by calculating CBV B inverse n minus CNBV. Okay. So this is our row 0 calculation. So let's go ahead and we can do that in Octave Online, and I'm going to have to look at both at the same time. So for starters, I'm just going to clear the screen using CLC and then clear all the variables so that I'm starting fresh. All right, so we said CBV is equal to 4 and 0. All right, CNBV is equal to 1 and 0. B is equal to 2, 0, 1, 1. N is equal to 1, 1, 2, 0. And then B, what is that equal to? 6 and 8. Okay, so let's go ahead and go through this first multiplication. And here I'm going to just write the inverse of B in line as a function. Right, so we get 1 and 2. Right. So that tells us we can put, after that calculation, we're going to fill in 1 and 2. All right. The next thing we want to fill in is, what is that all equal to? So we can just calculate what that is all equal to by multiplying CBV times B inverse B. All right, so let's go to Octave Online. Oh, oops, spelled inverse wrong. So that's going to be equal to 12. So we can fill in 12. All right, the next, so we have our 0 row, at least the important values. I guess technically there's a 1 right here or something. All right, so the next question is, what about the constraint rows? All right, so we're going to end up having 2 constraint rows here. Right. And again, remember, because we know x2 and s1 or x2 and s2 are our basic variables, we know what those columns are going to look like. They're just going to be 1, 0, and 0, 1. And now we just have to worry about filling in the rest of that table. All right. So again, the way we sort of fill it in is we use the equation that we had calculated above. So we're going to multiply the identity matrix. We don't really need it, but times XBV plus B inverse N XNBV. Okay, so technically we've already done this I XBV. That's what these columns correspond to. That's the I matrix, right? The 1, 0, and 0, 1. So we've got that. The only part that we really need to worry about is this part right here, the B inverse times N. So we can go ahead to octave, type in inverse B times N, and that's what we get. So we get 0.5, 1.5, and then 0.5 and negative 0.5. With that, we can just sort of plug those values into our table. So that's 1/2, negative 3/2, and then I think it was 1/2 and negative 1/2, right? Now, all that is equal to something, right? So what's the right-hand side? In this case, that's just given by B inverse B. So we get 3 and 5. And what you'll notice is what we're really calculating are the values for the non-basic variables in the simplex table or the simplex tableau. Because technically, if we know what the basic variables are, it's very easy to fill in those values. We know they're going to be 0 in row 0, and then for the remainder, it's going to look like the identity matrix. So that's how we would go about completing the simplex table for a given problem, assuming that we knew what the optimal basic variables were. Okay, so with that, we're going to take a little break, and let's reconvene at 2:50 p.m. Okay, so in about 7 minutes. And again, that's 2:50 by my time here on my clock. So, okay, guys, so we'll take a little break.
All right, so to review, what we're going to begin by doing is sort of framing out all the critical equations that we're going to use as part of any sensitivity analysis. So to start with, it's going to be a good idea to first recall how we structure our optimization problems. And so the way we want to think about it is we're going to be solving some maximization where we split the cost function or the objective function according to the basic variables and non-basic variables. Similarly, we're going to split the constraint equations based on the basic variables and non-basic variables. And finally, we'll have our non-negativity constraints, which still hold from before. Okay, now the way that I like to think about this is in the context of our Cplex or our Simplex Tableau. All right, so in the Simplex Tableau, we have a series of rows and decision variables. So up top, we might have our decision variables. Okay. And we'll have, various rows. So the first row, row 0, this corresponds to the cost. Okay. And then the subsequent rows from row 1 to row M, these correspond to the constraint equations. Now, so effectively in our Tableau, we have 4 different parts that we need to worry about. Okay. So the first part has to do with the coefficients of the objective function. All right. The next segment is, what is the objective value? And finally, we have the constraint equations, or the coefficients of the constraints. And again, these are in the form that we require, where we see a 0, 0, 0, 1, 0, 0, 0 for all our basic variables. And then for the non-basic variables, they can sort of be whatever values that we want. And finally, we have the right-hand side equations, or the right-hand side values of the constraint equations. All right, so these are the 4 different parts. Now, each one of these parts has a corresponding equation that we're going to use. So for row 0, for the cost, we have CBV times B inverse n minus CN BV. All right, and this ends up getting multiplied times XN BV. Okay, so this equation provides us with the coefficients of the non-basic variables in row 0. So that would be these coefficients. Now the coefficients for the basic variables end up just being 0. So we don't have to worry too much about that. All right. So the objective value then is given by CBV times B inverse B. All right. The constraint section, so this is row 1 to M, right? That's given by I, the identity matrix, times XBV plus B inverse N times XN BV. And the right-hand side is B inverse B. And so these are more or less the 4 equations that we're going to use when we're performing our sensitivity analysis. And again, they correspond to the 4 portions of the Simplex Tableau that we discussed over here. All right. Now, when we perform our sensitivity analysis, we're going to consider a few different things. All right. So typically what we're interested in is what happens if we change the objective function, or what happens if we change the right-hand side of the constraints, or maybe the coefficients of the constraints by adding a row or changing some parameters. Now, effectively, what we're going to look for, though, so the key outcomes that we want to, when we perform our sensitivity analysis, we're going to look for changes in the cost function, or specifically the changes in row 0. All right? And again, we're going to look for cases when row 0 changes to the parameters, introduce changes to row 0 so that we have negative values. Okay. We know that if we have negative values, then our basis variables are no longer, our selected basis variables are no longer optimal. And so that's what we're looking for. So when are our basis values no longer optimal? Well, it's whenever row 0 has negative values in it. So that's one place where we can check or perform a sensitivity analysis, right? The other place that we're going to sort of be observing changes to our problem and how they impact our formulation are in changes to the right-hand side of the constraints. The reason for this is our right-hand side constraint should always be positive. And if we see negative numbers introduced, then we know we have some sort of problem. Typically, that's associated with suboptimality or infeasibility or something sort of weird. And so that's what our sensitivity analysis will be checking for. Alrighty. So again, just to sort of hammer in this point, we know a set of basic variables is optimal if row 0 only has non-negative coefficients. Now, what we're going to do as part of the sensitivity analysis, we're going to check to see when row 0 when row 0 begins to have negative values. Similarly, we're going to check to see or make sure that the right-hand side of the Simplex Tableau remains positive. All right. Sometimes it's possible that changes to the constraints might make the right-hand side of the Simplex table negative. And so we're going to want to be cognizant of that. All right. Okay. Now, as part of our sensitivity analysis, we're going to study a few different basic problems or basic, I guess, sensitivity analysis, right? So the first one that we're going to look at has to do with CNBV. Right? So we'll look for changes to the objective function of the non-basic variables. And essentially what we want to see is, when do changes of CNBV, like if we make CNBV, larger value, when does it become, let's say, more profitable to change your basic variables and adjust your strategy, right? The next option we're going to sort of look at is what happens to changes to CBV. So just like changes to our non-basic variables might cause us to introduce those non-basic variables into, or turn non-basic variables into basic variables, the same thing might happen with CBV, right? So depending on if we increase certain coefficients, we might push out basic variables to non-basic. Similarly, if we decrease CBV, so certain coefficients, we might also lose additional basic variables. So these are the two main changes that we're going to look at when we're performing a sensitivity analysis. The next one, and mostly the third most important one, is we're going to look at changes to B. So this is the right-hand side coefficient. Okay, so over here. So these are the three main changes that we'll look at. The first sensitivity analysis that we're going to perform is to study what happens if we change CNBV, which is the cost coefficients related to the non-basic variables. And the way that we're going to go about doing that is we're going to look at the row 0, right, and we're going to replace our original CNBV with CNBV prime. Now, CNBV prime is just going to be our original CNBV plus some delta value in the ith column. Right? And so what we're going to want to do is we're going to want to check, when does row 0, right, with this new CNBV prime have any negative values? And again, we're doing this all within the context of the following optimization, where we break up our decision variables into the basic variables and the non-basic variables. And so more or less all we have to do is check for negative values in that equation that we have listed right here.
Crap. How long did that happen?
Since the break.
Yeah, since the break. Okay. I'll go. Thank you for telling me that. I'll re-record the part that I missed. But we'll sort of fill it in. I'll redo that part, so don't worry. Okay. All right. So let's sort of work through this by an example to see how this plays out, this change to delta. Okay, so you'll see I've already put in the slack variables for this problem. All right. And let's say, you know, we solved it and we already know what the optimal solution is. All right, so we already know the optimal basic feasible solution. This is all a given, okay? And in fact, I think, again, this is the same example problem that we're constantly doing. Okay, so it ends up these guys become your basic variables, right? So S1 is 24, X3 is 8, X1 is 2, and then everything else is 0. All right, so if we break down this problem into the format that we're used to, CBV is equal to 0, 20, and 60. CNBV is 30, 0, 0. And again, this is the same problem we've been already sort of playing around with. I'll go ahead and write B inverse because we've already solved for it. And again, you kind of can see I'm trying to organize it between basic variables and non-basic variables, but it's not so important. You can order it however you want. Okay, so these are all our matrices, right? And again, our goal is, well, let's say we wanted to figure out the sensitivity to one of these variables. Specifically, let's say, oops, I think this should be a 30. Let's say we wanted to figure out sensitivity to the cost of X2. So again, we're looking at what happens if we were to change this parameter. So before it was 30, but what if we made it bigger or smaller, right? What would happen? Okay, so again, we want to look at the row 0. So the equation that we're going to use is CBV times B inverse N minus. And normally we would use CNBV, but we're going to adjust it, right? Now we're going to use CNBV prime, and we want to see when this equation ends up being negative. So we're looking for any negative values. Okay, so what is CNBV prime? Well, we can sort of fill this stuff in. Let's start with that. So CNBV prime is, it's just going to start off with CNBV, which was 30, 0, 0. But now we're going to add in a delta corresponding to X2. Okay, so again, this is like the idea of, hey, we're going to start making our profit on slides. We're going to find a way to sell them for more money or make more money off of them. And so the question is, how does this delta need to change? Okay, so how much more do we need to increase this 30 value here to make it worthwhile for x2 to be non-zero? Okay. All right. So this first part, we can go ahead and multiply everything out to see what CBV times B inverse N is equal to. And I'll do this here. And let's see if I have these values already stored. I don't think I do. Oh. Yeah, there we go. CBV equals 20, 0, 20, 60. B in this case was equal to 1. Oops, does this have it saved? There goes B. And then finally, where's N? There goes N. All right, so we want to calculate what CBV times inverse B times N is equal to. So in this case, we get 35, 10, and 10. Right? So this quantity here is 35, 10, and 10. Right? And now what we're going to do is we're going to subtract off $30 plus delta, 0, 0. And we want to see when that subtraction, oops, and I'm missing, yeah, when that subtraction generates a negative number. All right, so putting this all together, we get 5 minus delta, 10, 10. All right. And the question is, for what values of delta here does this vector remain positive or become negative? All right, so we want to check for what values does the quantity remain positive. Okay. So basically, we're going to check when is 5 minus delta still greater than or equal to 0? Well, that occurs when delta is less than 5, less than or equal to 5. Okay. So as long as delta is less than or equal to 5, then the optimal basic variables won't change. Okay, so let's say, what does this mean? Well, if I change this 30 to 31, 33.5, even 35, right? X2 would still be equal to 0, okay? And in fact, all these guys would stay the same, right? Because X2 is 0, everything else remains the same, right? It doesn't change X1 and X3, right? It just doesn't make sense to adjust them. Okay. So that's sort of neat. Because X2 remains 0, X1 remains the same, X3 remains the same, S1 remains the same, and even Z, the objective value, remains the same. And we can actually see that. So if you look at our the summary, right, that we have right here, this is the objective value, okay? And you can see the objective value has nothing to do with CNBV, okay? It's just CBV of the basic variables. All right, so let's sort of write that out. So furthermore, so this is sort of a big point, all right? So if delta is less than or equal to 5, then x2 remains 0. Right? So it's still a non-basic variable, okay? The optimal solution, and the sort of corollary to that is the optimal solution of the basic variables remains the same. And from that, it follows, well, if the non-basic variables don't change and the basic variables stay the same, then the optimal cost, or the objective function, the optimal objective value remains the same. And again, and I know I write sort of slanted, we see that because Z, the objective value, is given by CBV times B inverse B. And you'll notice it's not a function of CNBV. Okay. So that's sort of neat. Our solution remains the same. Now, if delta ends up being bigger than 5, right, then in that case, our optimal basic variables will change. So our solution will completely change. And so this is telling us how much can you play with the non-basic variables and still get the same solution. Now, sometimes you can, the way we did this, we did it for just one non-basic variable. Sometimes you can do this for all the basic variables at the same time. You don't have to test them one at a time. Okay. So if you want, right, so sort of the linear algebra or the matrix algebra approach, you could do it all at once. You could take your CBV times B inverse times N, and you could subtract your CNBV plus a whole bunch of deltas, delta 1, delta 2, all the way to, it's going to end up being N minus M, right? So however many non-basic variables you have. So you could do this all at once. Now, in this case, this quantity, we already know that vector, right? So that just stays the same. So this is for the example. But I'm going to give you a little word of warning when you do this, so you just need to be careful. So here we'd subtract off 30 plus delta 1, we'd subtract off delta 2, and we'd subtract off delta 3. So when we do that, we get 5 minus delta 1, 10 minus delta 2, and 10 minus delta 3. And so it's pretty easy to figure out, for multiple deltas at the same time, when our optimal solution is no longer optimal, right? But we have to be a little bit careful, right? And the reason for that is not all the non-basic variables are actual decision variables. So this guy here corresponded to x2, and I'll put that as well here. The second coefficient, I believe, corresponds to, what is it, S1 maybe? Let me check. No, S2. So this coefficient actually corresponds to S2. And finally, the last coefficient corresponds to S3. Now remember, these slack variables, they don't really mean anything, okay? They're not like, they don't have meaning. We just use them in order to get into standard form. So they don't actually have a cost. There's no like, if we're again producing toys, then the decision variables are how many trains do we produce? How many soldiers do we produce? How many slides do we produce? The slack variables don't have that same meaning. Okay. So whenever you perform a sensitivity analysis, you don't perform it on slack variables. Okay. So only perform sensitivity analysis on the primary decision variables. So these are the original decision variables. So never on the slack. Okay. All right. That's kind of neat. Okay, so we learned how to do a sensitivity analysis when we change the cost coefficient for a non-basic variable. All right. The next type of sensitivity analysis that we can do is we can say, hey, what if we change the cost coefficient of a basic variable? So let's say for some reason material prices went up and we no longer get the same profit anymore, right? Do we still have the same optimal solution, or at least the same optimal basic variables, where our strategy is to make toy soldiers and toy trains? Or should we just start making toy trains because the profit margins on the soldiers decreased? All right, so that's the sort of question that we'd ask. And again, you're going to use the same approach here, all right? So we think about how does the row 0 change for a change in the CBV. Okay, so originally the equation for our row 0 so the original equation again is CBV times B inverse N minus CNBV. And we're going to change this CBV guy. Okay. And the way that we're going to change it is similar to before. So we're going to define the CBV prime, and it's going to be equal to whatever our original cost coefficients were, right? But then we're going to add some delta values to it. So again, we can sort of do multiple of these at the same time. And we're going to have M possible basic variables, okay? All right. So in this case, what we're looking at is what does C prime BV, oops, come on, stop, times B inverse N minus CNBV. So are there any negative values in this quantity? So that's what we want to do. All right. So we can sort of plug in or substitute what we had before. All right. So instead of C prime, we can just write CBV plus the deltas. All right. And we're going to multiply that whole quantity times B inverse N minus C and BV. Okay. Doing a little bit more manipulation. So if we multiply stuff out and we're going to group it, so I'm going to get CBV times B inverse N minus CNBV. All right. So basically I'm pulling out this stuff altogether. All right. Plus, and then we're going to have the deltas sort of separated. Now, this part is the original row 0. Okay, this is what we started off with. So in our case, right, so if we want to go back, oops, lost connectivity. That seems weird. Yeah. So in this case, we've already calculated what CBV times B inverse N is equal to. Yeah, we got that. All right. So that's just equal to 35, 10, 10. All right. But now we want to subtract off the CNBV, which was equal to 30, 0, 0. Right, so that whole quantity is the red portion. And we still have this delta 1 to delta M times B inverse N. Now we can go ahead and do that multiplication. In fact, I think we've done it before. So I'm going to just go ahead and we have the values of B inverse and N. So I'll go ahead and plug those in. All right. So this is what we have so far. And so, of course, we can do a simplification with the vectors on the left. Right? That just gives us 5, 10, and 10. All right. But now we have this matrix multiplication. And things get a little bit messy. But we can sort of figure it out.
Bella,
Yeah.
do we have to add the part for delta or subtract? Because the first equation with the red line with original 0, you added here, add
Oh,
delta.
yeah, it needs to be an addition. Yeah, remains an addition. Yeah, so there's a plus. Thank you. Okay. So in fact, what I'm going to do is to save a little bit of space because the way this is written, instead of writing this as a row vector, I'm going to transpose it and write it as a column vector. Right? And again, this is just to make life a little bit cleaner. And you'll see why. Because what we need to do is multiply these two matrices together. Right? And so if you go through this multiplication, you end up with the following. Okay. So you end up with minus 2 delta 1, minus 2 delta 1, and no. Sorry, I did that wrong. Row times column, row times column, row times column. Oh, okay. Yeah. So minus 2 delta 2 plus 1.25 delta 3. Okay. It should be 3. Okay. And again, we're doing it for this particular example. So this is not a like, there's a singular value right here. So there's like 5 when you do all the math, right? The next row corresponds to 2 delta 1. Plus 2 delta 2 minus 0.5 delta 3. Right? And then finally, we have the last row, which is just, row times column. That's the idea. So we have minus 8 delta 1, minus 4 delta 2, plus 1.5 delta 3. Okay, so these are, we're going to have 3 values that we're going to want to check. Right? And again, we're only interested in changing values corresponding to our original decision variables. Okay, so our original decision variables were x1, x2, and x3. All right, and then we had slack variables s1, s2, and s3 for this problem. Now it ends up that the only if we want to figure out what our basic variables are, they were x1, x3, and s1. Okay, so we only have of our decision variables that are basic variables. The only corresponding ones are x1 and x3. Okay, so we're not going to be able to, it doesn't make sense to change CBV for S1, right? Because that's a slack variable. It's like a pretend variable. Okay, so we only want to figure out what happens if we change the delta corresponding to the X1 decision variable or the delta corresponding to the X3 decision variable. Okay, so in this case, if you guys remember, our XBV was S1, X3, and X1. So it was a little bit out of order, right? So that what that means is if we wiggle the cost equation related to X3, right, that actually corresponds to delta 2. And that's because it's the second element in XBV. Okay. And for X1, what we're doing is we're actually wiggling the third value. Okay, so that's going to be delta 3. Now we don't worry about delta 1 because that corresponds to the S1 slack variable. Okay. All right. So we can sort of play this game of, hey, how does changing X2 adjust this equation? And then how does changing delta 3 affect that equation as well? All right. So let's pretend we adjusted the coefficient for X3. Okay, so that corresponds to delta 2. Okay, and so what we want to do is, and we're going to assume delta 1 and delta 3 are 0. Okay, so if we do that and we pick out these equations, we're going to end up with 5 minus 2 delta 2 is one equation. The other equation is 10 plus 2 delta 2. And the last equation is 10 minus 4 delta 2. Okay, so this ends up being the row, the 0 row coefficients if we wiggle delta 2, right? So the coefficient corresponding to X3. And what we want to check is when are these values, right? The corresponding values all greater than 0. Okay, so the way that we could write that is we're going to say 5 minus 2 delta 2 is greater than or equal to 0. 10 plus 2 delta 2 is greater than or equal to 0. And finally, 10 minus 4 delta 2 is greater than or equal to 0. So we want to figure out what values of delta does that correspond to. And so in this case, we can just solve for delta or get the delta on one side. So in this first case, we'd end up with 5/2, or delta 2 has to be greater than or equal, or less than or equal to 5/2. Okay. For the next equation, we end up with delta 2 has to be greater than or equal to 5. Right? And in this last case, we end up with, so if we move delta to the other side, 10/4 is 5/2 is less than or equal to delta 2. All right, so all these have to be true at the same time in order for our basic variables, our optimal basic variables, to remain the same. So what we can do is sort of draw this on a number line. All right, so we have 5/2 here. We'll put 0 there and negative. Oops, and that should be a negative there, -5 there. All right, so we know delta 2 has to be greater than -5, right? But not only that, delta 2 has to be less than 5/2. So what this tells us is that as long as delta 2 is between 5 halves and -5, right? So when delta 2 is between -5 halves and 5, then the optimal basic variables remains the same. Okay. So if delta 2 ever becomes more negative or more positive, then our solution will change, right? So in this case, if delta 2 becomes negative, right, or it loses value, right, then what that means is maybe we shouldn't make toy trains anymore, right? So one way we'd stop making toy trains, right, is if we don't make as much profit anymore. Alternatively, our solution might change if the profit of toy trains becomes really big, right? What if the profit of toy trains becomes so big, we say, well, let's just only focus on trains. We're not going to make toy soldiers anymore, right? So that's why it's not uncommon to see a range of values, right? It's not just how much can we decrease or how much can we increase. It might be bounded below and above. Okay. All right. So we could do a similar approach for x1, right? So we can adjust the coefficient for x1. And again, this corresponds to delta 3. Okay, so here we're only going to change delta 3. Right? And so we want to pull out all these equations, right? The parts of the equation that have delta 3 in them. Right? And we're going to assume delta 2 and delta 1 are 0. And we're going to keep this 5, 10, 10. Right? So we can write those equations as they show up. So we should get 5 plus 1.25 delta 3. And we want to make sure that's still greater than 0. We also have 5 minus 0.5 delta 3 is greater than or equal to 0. And finally, 10 plus 1.5 delta 3 is greater than or equal to 0. So we're going to take the same approach where we just try to get delta 3 on one side. If we do that, we end up with delta 3 has to be greater than or equal to 4. Wait, is that right? Yeah. No. Negative 4, sorry. That seemed, something about that seemed off. All right, so delta 3 has to be greater than or equal to negative 4. For the next equation, we get delta 3 has to be less than or equal to 20. And then finally, delta 3 is greater than or equal to negative 6.666, right? So sort of repeating. All right, so again, we can sort of take the same approach with the number line. So we have 20, 0, negative 4, and negative 6.6. Now, it has to be the intersection of the three sets, right? So the first set is, everything less than negative 20, right? The next set is everything greater than negative 4. And then finally, everything greater than negative 6.6. And the only region that they have in common, or the region that they have in common, is right here. Okay, so where they're all the same, right? So in that case, that tells us that delta 3 has to be between negative 4 and 20 in order for our basic variables to remain the same. Okay. So the basic variables remain optimal. Okay. Now, if delta 3 is not inside of that set, so if it's not between -4 and 20, so it's not, then what that means is we have to perform the simplex process in order to find the new entering variable and the exiting variable. So again, the basic idea is that the basic variables will change. Okay. Now, with a change in the CBV, we should expect a change to the objective function, right? And so there will be a change, right? Because again, objective, so the objective value, the Z, right? Well, that's given by CBV times I always like looking it up on my table. I sort of keep that. So remember, the objective value is CBV times B inverse B. So if we change CBV, right? So originally, this is what we had. But if we change CBV to have the deltas, right? Okay, so we want to figure, well, if I change the cost, how does that change my optimal solution? We can actually just figure that out here, and it ends up being pretty simple. So it ends up being whatever our original optimal value was, our original optimal objective function, plus whatever that delta change was. Oops. Times B inverse B, okay? So we can calculate the change to the objective value if we wiggle one of the parameters a little bit. So this is kind of neat. So just because you increase the C, the coefficient by 1, doesn't mean that you're going to get, you know, a linear increase by that 1, right? So like, let's say before you were making 10 trains, right, as your optimal solution. And you said, hey, instead of charging $10 for 10 trains, I'm going to charge $11, right? So I'm going to increase my sale price by $1. You would think, oh, maybe I'll make, you know, 1 times 10 more dollars, right? So originally you were making $100 on trains. Now you're going to make $110 on trains. That's not quite how it works out, because if you increase your price of trains, that might decrease, you know, that might sort of wreak a little havoc. You might end up selling less trains than before and producing more toy soldiers. And so we see that interaction by the right-hand side of this equation, by the B inverse B. Okay, so this is sort of something that you need to be a little bit careful of. So, you know, if you're ever doing, you know, you're like, oh, I'm just going to change how much I charge for a product that we sell, and it's not going to adjust, you know, our total sales. No, that's not right. You know, you could actually even make things worse. So for example, this right-hand side could end up being negative. So just, food for thought, I guess. The idea is if you raise your prices, you could actually decrease your profits in some way. So that's sort of neat. Okay. So we figured out what happens when we have a change to our cost coefficient in the basic variables. We also, and before that, we figure out, what happens if we change our non-basic variables. The next sort of question that we're going to ask is what happens if we change our right-hand side coefficient B. Okay. Now, there's two things that we need to be careful of. So the first one is when we change B. So again, we're going to have our original B. But we're going to change it by some delta value. Okay. Now there's just one rule, which is if we go back to our summary equations, right? So this is, weird. This is the equation we're going to look at first. So this B inverse B in our simplex table. All right. We need to make sure that B inverse B prime remains greater than or equal to 0. All right. So if that doesn't happen, then that means our optimal basis is no longer correct. Okay. So that's the first thing that we need to check. All right. And so we could do this pretty quickly. So in the example problem, we already know our B inverse. So that's 1, 2, 8, 0, 0, 2. Right. And we know our original B. Right. So the question is, how much can we change this B? We're going to add some delta values or subtract some delta values. Okay. And again, it's sort of using this equation here. All right. So let's go through this. Well, what is B inverse times B prime? Well, that's equal to B inverse times B plus the vector of deltas. And again, usually we just change one of these at a time. So we only consider one of the deltas to be non-zero and the rest are 0. So that's usually how it works out. But you could do multiple deltas at the same time, but you just have to be a little bit careful of tracking it. Well, if we go through that multiplication, we get B inverse B plus B inverse times the deltas. Okay. So we already know this first quantity. This is just from our optimal simplex table to the original problem. And then we have our B inverse times the delta. So we can sort of fill this in. And in this case, we only have M equations. So we have delta 1, delta 2, and delta 3. So we can go ahead and go through these multiplications, right? So if you multiply all these equations out, you get 24 plus, again, row times column, delta 1 plus 2 delta 2 plus 8 delta 3, 8 plus 2 delta 2 minus 4 delta 3, And finally 4 plus 1/2 delta 2 plus 1.5 delta 3. Okay, so these are the three equations that you need to be careful of. And you need to make sure that each one of these rows remains greater than 0. So let's sort of see how much we can wiggle each one of them individually. Okay. All right, so let's say we wanted to change the second constraint. So before, we had the value of 20, okay? And we want to say, hey, can we increase or decrease that right-hand side equation, and how much can we change it? Okay, so let's say delta 1 is equal to 0 and delta 3 is equal to 0. Then these equations sort of simplify to 24 plus 2 delta 2 is greater than or equal to 0. 8 plus 2 delta 2 is greater than or equal to 0. And finally, 4 plus 1/2 delta 2 is greater than or equal to 0. So we want to figure out what range of delta 2 satisfy these equations simultaneously. Okay. So if we solve for delta 2 in each case, in this first case, we get delta 2 is less than 12. In the second case, we get delta 2 is greater than -4. And in the last case, I think I might have done something wrong. I have a different value in my notes for some reason. Sorry, just to be clear, this should have been a 2, not a 4. Doesn't really change the overall analysis. Okay. And this is just to keep track with the original. This is the same problem we're always working with. So if we solve for delta 2 in this case, and in fact, there's another mistake here. Geez, man. It's a minus B inverse. Yeah, minus. Okay. If we solve for delta 2 in this case, we end up that delta 2 has to be less than or equal to 4. Okay, so again, if we want to draw this on the number line, we have 12, 4, let's say 0, and 4, -4. All right, so delta 2 has to be less than 12. Delta 2 has to be less than 4. But at the same time, delta 2 has to be greater than -4. And so the only area that sort of satisfies all three of those constraints is that delta 2 has to be between, so these three equations, and for that delta 2 has to be between 4 and -4. So for our sensitivity analysis, this is the range for which our optimal basis variables or basic variables remain the same. Okay. Now, if the delta 2 has to be between -4 and 4, that tells us, so again, let's say delta 2 is between -4 and 4. Okay. So how does that correspond to the coefficient? Okay, so before we said our coefficient, the value was 20. Okay, so now that means we just apply delta to it. The range of B2, well, that has to be between 24 and 16. Okay, so delta tells us how much we can change it. And then if we apply that to B, that gives us the upper and lower range for the values. Now, similarly, keep in mind that if you change the right-hand side to the equation, that changes the objective value. Okay. Because we know the objective value, the optimal objective value, well, that's equal to CBV times B inverse. And in this case, we're going to plug in B prime. So whatever this new B prime is, we can figure out how that adjusts our optimal objective value. Now, one thing that we can do, so in the last lecture, we discussed the idea of shadow prices. Okay. So shadow prices were the change in the objective function, or objective value, sorry, to a unit change on the right-hand side. Okay, so this is delta. And effectively, the way that you can calculate this is you can set the delta. So let's say you want to figure out how your delta changes. Okay, so, you know, in this case, let's say our second constraint equation, we want to change it from 20 to 21. Okay, so what we would write in is, or what we'd calculate is CBV, B inverse, and then we substitute in whatever that delta is, right? So the delta is going to look something like 0, 0, 0, 1, 0, 0. You know, there's only going to be one value that we select, okay? And so what we can do is we can just say, well, if I want to figure out what the shadow prices are, it's the change in the objective value, okay? Okay. So this part doesn't matter, so we can sort of ignore that. Okay, and this result, so if this is the ith row, okay, then calculating this value of CBV B inverse times 0, 0, 0, 0, 0, 1 for that ith row, right? This corresponds, this is the shadow price for the ith constraint. Okay, and again, it tells us if we increase the ith constraint, the right-hand side, by a value of 1, how does that change our objective function? Okay. So this is kind of a neat little way we can calculate the objective function pretty quickly. All right, so we're going to do 2 more types of sensitivity analysis that we can perform, and then we'll end with that. The first is changing the constraints and cost for a non-basic variable. Okay. What do I mean by that? Yeah, okay. So let's say, so we actually did part of this, so maybe we don't really need to do it. We already did the change for a cost, right? But let's say we change the constraints for a non-basic variable. Okay. So what do I mean by that? So again, let's say we had our optimization, and I'm going to write it in sort of the matrix form. right? What if I said one day, oh, I got all the parameters wrong in the original formulation for the costs associated with trains, right? This was wrong, and that was wrong. Instead of 6, maybe it's 5. Okay. Maybe this guy stayed the same, but maybe 1.5 became 2. Whatever it was, we saw a change in that matrix. And we could ask the question pretty easily, well, does this change in the A matrix, right, for a non-basic variable? So in this case, again, we're working with the same problem. The basic variables were x1, x3, and s1. And then the non-basic variables were x2, s2, and s3. Okay, so NBV. And then these guys were basic variables. Okay. So the question is, if I change the A matrix, right, for just one of the non-basic variables, all the coefficients, is there a change in my optimal basic variables? And, in this case, all we have to do is check. Well, let's look at that row 0. Okay, so we're going to look at CBV times B inverse and whatever the new n prime is. Okay, minus CNBV. Okay, so this change right here is going to get integrated into n prime, right? And we want to check to see if now we have negative coefficients in this calculation. It's a little bit harder to get nice clean equations for this because you're doing like matrix multiplications of B inverse times n prime, but you can sort of do it if you wanted to, right? You could work through the same math that we did. So if negative values appear in row 0, then we're no longer optimal, right? So if you made a change to your problem because you got new information, then that would be it. Okay. The other type of standard sort of sensitivity analysis that's often done is adding a new activity. Okay. This is the same thing as just adding a new constraint, or sorry, a new decision variable. Okay. So again, maybe we had this, I'm going to copy this. Oh, no, I can't copy that. Dang it. We'll see. I'm going to give it a shot. All right, so this was our original problem. Again, maybe we're making toy soldiers, toy trains, and toy slides, right? And then one day somebody goes, hey, why don't we start making cell phones? Okay. And so the idea is you're going to change your decision variables to now include another decision variable corresponding to making cell phones, right? So maybe in the process of doing that, you say, well, in making new cell phones, I can, my profit will be $500 per new cell phone. Okay. But I still might have new constraints associated, I'm still going to have to include the constraints associated with now making cell phones because I still have material costs, labor costs, overtime costs. Okay. So that means we're going to be adding a new column here. Okay. So the idea of adding a new activity is like adding a new decision variable. Okay. And so it's going to come up in 2 ways. 1, our cost function is going to change. And 2, our constraint equations are also going to change. Now, the first assumption we're going to make, so we're going to assume this new activity is part of the non-basic variables. So somebody says, hey, we could make cell phones. Okay, cool. We expect to make $500 cell phone, but maybe it introduces a bunch of constraints associated with that. Okay. The starting assumption is that the option to make cell phones doesn't get exercised. Okay. So that decision variable is going to be a non-basic variable, but we can still calculate. What we then do is we calculate CBV times B inverse times N prime. So this N prime, again, it's going to correspond to all of the, and I'll sort of highlight it. All right, so it's the columns of our original non-basic variables, but now we're going to augment it with the new column that we introduced by making cell phones, right? And we subtract that from CNBV prime, right? And CNBV prime, again, it's just our old CNBV, which included 30, 0, and 0, but now it's also going to include 500. And so you want to go through that calculation, and you're going to check if after doing this calculation has any negative coefficients, that quantity. Right? So if it has negative coefficients, then that means your basic variables are no longer the same, right? So you might actually end up saying, hey, I got to build cell phones now, right? Because I'm going to make too much money. Okay, with that, we are going to wrap up lecture. So we'll finish up our sensitivity analysis. Again, I've posted a bunch of videos on Cplex. And so to make up for, I think we have about 10 more minutes of lecture. What I want you to do is to install Cplex. And then there's a video on like my first Cplex program, all right, or my first LP using Cplex. Please go ahead and watch that video. You should be able to find it in web courses. Let's see if I can show you where that is. So if you go to the modules, again, this is what I see. Let me see if I can put it into student view. Hopefully you see something like this. Go ahead and, oh, where is it? Oh, this is out of order. Okay, I guess I'm missing it, right? So I'll put a video here that says something like my first linear program. And so please go ahead and watch that video, or at least I'll put an announcement with a link. And so that will get you at least learning how to program very simple LPs using Cplex. And again, this will help you when you do your sensitivity analysis, or in the future, if they ever ask you, hey, solve this optimization, then you'll do it using Cplex. Okay, that's it for now. Thank you all. If you have any questions, feel free to speak up. Otherwise, I'll talk to you later.
Thank you, Dr. Vela.
Yep. See you all soon.
Thank you, Professor.
Thank you very much.
Thank you. Have a good one.
Right. All right. If there's no questions, I'm going to go. See y'all.